Okay, guys, so we're dealing with waves, okay? And so we need to understand something about waves before we can understand how waves interact with matter. So as we look at waves, okay, we want to think about what waves do when they meet each other. One of the neat things about waves is when waves meet each other, they can pass through each other. So if I had a wave that was traveling in this direction, and it met a second wave that was traveling in the opposite direction. Okay, so they're coming out at each other, and they meet here at a location in space. When they meet, they can pass through each other. But where they meet, well, let me draw this in a different way for you. Let's say that I have a wave pulse. It looks like this and is traveling in this direction. And over here, I have another wave pulse. And they're traveling toward each other. Okay, when those wave pulses meet, so let's kind of look at them meeting here. Let's say when they first meet, okay, I can get a real funky looking thing like this where they start to overlap each other. And then down the road, okay, when they're both sitting on top of each other, I get a nice double fat. Let's see, that was that. So that, I'm going to have to draw way down low here. I get a really tall. And then once they've passed past each other, they move through and go on. So you could think of this as image 1. Here, that's image 2, 3, 4. Waves pass through each other. And where they meet, you get a combination disturbance. Okay? Now, where they meet at that common point, we call that interaction interference. And interference can be constructive or destructive. Now, constructive interference, they add together to give something bigger. Than the individual waves. What I was drawing before was constructive interference. I got something bigger. Destructive means that they add together to cancel each other out. Okay? So it destroys. Constructive adds, destructive destroys. Now, if we think about it, if the waves are in phase with each other, they're doing the same thing at the same time, then I get something that's a lot bigger. Constructive interference. If the waves are doing opposite at the same time, I get destructive and they cancel each other out. Okay? Constructive interference, destructive interference. Now, prettier pictures in my notes, but, you know, I always have to draw. Now, waves also show something called a diffraction pattern, or an interference pattern, and occurs when waves encounter very tiny openings that are about the width of a wavelength. So if I have, let's say, a wall here, and I put two openings in the wall. And over here I have a screen. Okay? Now, if we were to have waves coming in at this wall, think about being in a helicopter flying, right next to the shore, and you can watch the crests of the waves coming in. Okay? When they meet these openings, something really interesting happens. When they come out the other side, we get, I'm not drawing them super evenly, so forgive me. They come out curved. Okay? Now, same thing happens here. If I look at this spot right here, and I think about the two waves meeting, at that spot right there, they're doing the same thing at the same time. This is constructive interference. If I'm at a spot right here, okay, this wave is going up, but this wave is going down. This would be destructive interference. Constructive, destructive. Okay? So we've got constructive and destructive interference going on. Now, I've got a pretty picture of what happens as the wave goes through the opening, okay, in your notes. So let me show you, okay. When the wave moves through the opening, it bends and gives us a curved wavefront on the other side. That's referred to as diffraction, okay. Waves do that, particles do not. If I were to fire BBs at those openings, they would pass straight through. Okay? Now, when we do two or more slits, we're going to get a light or dark pattern on the screen. Places where we have constructive interference and destructive interference. Now, pretty picture in your notes. Okay, you can see it right here. Now I'm going to try to show this to you with my drawing. So if I were to draw an up and down line here, grab a ruler. Let's use a ruler to make an up and down line. Okay, so if I make an up and down line here, at this spot right here on my screen, I get a nice bright spot. There I'd have a dead spot. Let's see. So if I came down here where crest meets crest again, I get a bright spot. So we have a pattern of bright spots, dark spots, bright spots, dark spots. That's what's called an interference pattern, because I can see where the wave is adding together constructively and destructively. Light shows interference patterns, particles do not. Okay? Something else that light does that particles do not is refract. Refraction is the bending of the pathway traveled when light, and I'm using light generically for all electromagnetic radiation, encounters a new material you could also call it a medium, to the surface. Okay, what does that mean? Let's say I had a blocks of plexiglass here. Okay, I have plexiglass. Now, one of the ways that in physics, okay, we represent light is we'll draw an arrow showing the pathway that light is traveling. Think of it kind of like a laser beam. If I were to shoot a laser straight on at this piece of plexiglass, it would go straight through. But if I shot it at an angle, okay, so it hit at an angle like this, what we'd see is it would bend. That would be the straight line pathway, but this is the pathway the light actually took. Okay? And then when I get to this point right here, it bends again. This is referred to as refraction. Light does this, particles don't. So if we had a pool of water here, let me draw a pool here near the center. Okay, so if I had a pool of water, water, okay? If I were to throw a rock, I threw it here, it hits the surface of the water, it would follow kind of a curved pathway until it got to going straight down, it would go straight down. That's what particles do. If I were to shoot light at this, okay, immediately at the surface, it would change direction of travel and travel down. So refraction, okay? So particles follow a trajectory, and it's going to be a curved pathway. Light will follow a straight line pathway, counter new material. It immediately changes directions of travel and follows a new straight line pathway. All right? So refraction. Refraction is what allows the telescope to work, my glasses to work, binoculars to work.
Is there ever a time when light acts as particles? I've heard that somewhere.
We're getting there.
Okay.
So right now we're looking at the start of the 20th century and where the division was between matter and energy. And light was definitely in the energy category, and things like atoms were definitely in the particle category. Protons, neutrons, and electrons were considered particles. Light was considered energy. Okay? So, at the beginning of the 20th century, there were three phenomena that were just not explainable using classical physics with the clear demarcation between particles and energy. And the three phenomena we're going to look at is black body radiation, the photoelectric effect, and line spectra. We're going to do a lab on line spectra. Okay, so you're going to get to see one of these phenomena. Black body radiation, I can show you a demo for that. Photoelectric effect, that's what makes solar panels work. My calculator works off the photoelectric effect. Okay, so black body radiation, photoelectric effect, and line spectra. These were three things that physicists were having trouble explaining. So let's start off with black body radiation. Okay? Black body radiation is light given off by objects that are heated. Okay? Light is a form of radiation given off by heated objects. Now, think about a charcoal briquette that's hot. Okay, it glows. If you think about the filament inside a filament light bulb, it glows. Space heaters, old space heaters have nichrome wire in them, and as they heat up, they glow. Now, they didn't have any trouble with the fact that hot objects glowed, okay? Think about a potbelly stove that's gotten overly hot, it'll glow. They didn't have any trouble with the fact that it was giving off energy in the form of light as well as heat. What bothered them was the pattern of colors. Instead of kind of growing all the way through the kind of rainbow, there were only certain colors of light given off. So our problem, our question, is why are there only certain colors of light given off? Okay, they start out glowing a kind of a yellowy orange color, and it's kind of dim. And then they will go a more intense red. And eventually these objects will go what we call white hot. Okay? The question is why? Why do they go through this pattern of colors? Now, a scientist by the name of Planck was studying black body radiation. And he said, classical physics isn't cutting it. I need to go off the reservation. I need to think outside the box. And Planck said, you know, what if there were only certain allowable energy states for the object? He said, really, only certain allowable energy states for the atom that make up the objects. So Planck proposes only certain allowable energy states for atoms. This means that energy is quantized. Energy of an atom is quantized. You either have this much energy or this much energy, but no energy value in between. So this is the first time that we start to attribute a chunk nature to energy. Okay? This is a big deal. Really big deal. Okay? So, we want to acknowledge Planck. So Planck says energy of an atom is quantized. Now, at the same time Planck was playing with this, another scientist who was kind of tweedling around in obscurity, working as a patent clerk, was looking at the photoelectric effect. Okay? Now, the photoelectric effect is the creation of electricity by shining light on a metal. They were looking at zinc at the time. And so you had this hunk of metal, zinc, and we shine light on it. Light bulb. Okay? Light's coming down. And they hooked wires and an amp meter to two sides of the piece of zinc. So hook in here, hook in here. When they shine the light on this, they could get the ammeter to read a current. Showed a current. Now, again, light energy interacting with a metal, getting another form of energy, electricity, didn't bother them too much. So we got the photoelectric effect. But there were some things about the photoelectric effect that didn't make good sense. Okay? What they expected to see here is when they shined light on the zinc, that there would be kind of lag time for the zinc to kind of collect up energy to cause the current to flow. What they didn't expect is the fact that it's wavelength dependent. You could only get a current to flow if you were at a specific frequency of light or above. If you were below that frequency, no matter how bright the light was and how long you waited, you didn't see a current. The other thing is when you hit the right wavelength of the right frequency of light, you immediately got a current. There was no lag time once you hit the right frequency. Okay? And if you used bright light at the right frequency, you got a larger current. Dim light, you got less of a current. But it didn't occur at other wavelengths. You got to be, or frequencies. You got to be at the right frequency or above, or it was a no-go. Now, this was really driving physicists crazy because it should, according to classical physics, just collect up energy, and eventually you got a current to flow. And no matter what the wavelength was, the brighter the light, the faster the current should build up and start, and the higher the current should be. Dim light, lower current. The frequency dependency of this was really driving them crazy. Okay? So we got to have an explanation for this. Now this is where I'm going to stop, and we'll pick up here next time talking about Einstein's approach to this and how he played off Planck's work.